In this video, we are going to learn how to find the local extrema and saddle points for functions of two variables. Local extrema being either a local maximum or a local minimum, similar to the work we did in single variable calculus. Saddle points are a new type of point that arises as we extend into 3-space. Before we do any of that, we have to start with critical points. So a point AB is called a critical point. Critical point of a two-variable function, f of x, y, if one of the following is true. So the first thing that could be true is that the first order partial with respect to x at the point AB is equal to 0, and the first order partial with respect to y at that same point is also equal to 0. This is essentially the extension of setting the first derivative equal to 0 to find any critical points. We have two first order partial derivatives now, so we have to set both of them equal to 0. We can express this a little bit more compactly using the gradient vector. So we could express this as the gradient of the function at the point AB being equal to the 0 vector. They mean the same thing, just a bit more compact to use the gradient as opposed to the first order partials. But essentially we come to the same conclusion. The other possibility is that the first order partial with respect to x at the point AB, or the first order partial with respect to y at that point, is undefined. So we just also have to consider any points that would make either first order partial derivative undefined and consider them to be critical points as well. Happens less often. Most of the time we're going to be focused on this first requirement, but just something to keep in mind. So find the critical points of the function f of xy being equal to x cubed minus 6xy plus y squared. We'll start by finding both first order partial derivatives. So 3x squared minus 6y, and partial with respect to y, negative 6x plus 2y. Set both of these equal to 0 and solve. So looking at both of these, substitution will help us here. So I'll start with the partial with respect to y. So we could say 2y equals 6x and y equals 3x. So in order for this partial to be equal to 0, y has to be equal to 3x. So we'll substitute that in to our partial with respect to x. So substituting in the 3x and solving, so we can factor. We'll multiply out. I'll be a little bit more methodical here, and then taking a greatest common factor out. 3x times x minus 6 equals 0. So either x equals 0 or x equals 6. So that means we have two critical points at either x equals 0 or x equals 6. So critical points, we'll list them out. So if x is 0, remember y has to be equal to 3x, so that makes y 0. And then if x is 6, y would be 18. So these are the critical points of this function. We don't know how to classify them yet. We will, but these are the two critical points that we have to consider. Now, Fermat's theorem helps us here. Suppose both the first order partial with respect to x at the point AB and the first order partial with respect to y at AB exist. So we have first order partials that exist at the point AB. If the function f of xy has a local extrema at the point AB, then AB is a critical point of the function. Now, might not seem as important upon the first read-through, but this theorem is important in telling us whatever critical points we find, those are the only possibilities for our local extrema or saddle points. We don't have to look elsewhere, which saves us a lot of effort. Okay, so find your critical points. That's the only list of points that we have to consider moving into our next. So how do we classify points? So a function of two variables has a local minimum at the point AB if the function is always greater than or equal to the function at AB for all points x, y in some region around AB. So essentially, there's points around AB that all have function outputs that are greater than or equal to the function output at AB. right? And the reason it says some region, because a local minimum doesn't necessarily have to be the lowest point on the surface. It just has to be the lowest point on the surface in some restricted domain. Then we can say it has a local maximum at the point AB if the function is always less than or equal to the function at AB for all points in the region around AB. And then the last classification is the new one, which is a saddle point. A saddle point at the point AB if AB is a critical point of the function but does not have a local extrema at the point. So have some surfaces here to help us visualize what these look like. So in the first example, the origin is a local minimum. It also happens to be a absolute minimum rather. I tried to simplify the surface, but a local minimum means that there could be other points on the surface that are lower. But in this general region, that would be the lowest point. In the middle, we have a local maximum. Also happens to be an absolute maximum of the surface. And then here, if you recall this graph, this is the graph of the hyperbolic paraboloid. And right there at the origin, that's what we consider to be a saddle point. If you look at the trace going this way, it's concave up. But if you were to look at the trace parallel to the x-axis, it would be concave down. Right? So different traces or different cross-sections would have different concavity, and that results in the point being classified as a saddle point. Whereas, just for comparison, if you drew any cross-section through this point, every cross-section would be concave down. And similarly, if you took cross-sections through this point, every cross-section through that point would be concave up. Now, that's relevant for the way we will classify these points, which is the second derivative test. So the second derivative test builds off of the second derivative test from single variable calculus. Now, just to point out, second derivative test in single variable calculus is not used as frequently because oftentimes you are using a number line test to classify a point as either a local maximum or a local minimum because you get other information. The number line test does not extend nicely. We'd have way too many number lines to consider, so the second derivative test becomes more important to us. So what does the second derivative test say? Suppose that the second order partial derivatives of the function f of xy are continuous on an open disk around the point AB, for which the gradient of the function at AB is equal to the zero vector. So remember, this is just saying our first order partial derivatives at the point are equal to 0. We're going to define D as the second order partial with respect to only x at the point AB times the second order partial with respect to only y at the point AB minus the mixed second order partial, so in this case x then y, at the point AB, and we're going to square that. Now, just looking at this expression, the mixed order, the reason we're squaring it is Clause's theorem says that the mixed order partial x then y or y then x will be equal. So instead of writing xy times yx, we can abbreviate it and just say that the mixed partial is being squared. So the value of this expression will help us classify a point as a local extrema or a saddle point. Now, the nice part about this expression, it can be represented as the determinant of a 2x2 matrix. So let's draw that matrix over here. So we can create a 2x2 matrix. So partial with respect to x then x, partial with respect to x then y, partial with respect to y then x, y then y. So those are the 4 possible second order partial derivatives. We organize them in a 2x2 matrix. We take the determinant of that matrix and we get D. Okay, this is called a Hessian matrix. Makes it really easy. Instead of trying to memorize this formula, we can just memorize this setup and then go through the determinant each time. Now, The reason this helps classify everything is we're talking about second order derivatives. So if the value of d is positive, and the second order partial with respect to only x is also positive, so what this means is the trace parallel to the x-axis is concave up. That means that the point AB is a local minimum. Local minimum. So just to dive deeper for a moment here, when the d value is positive, what that is telling us is that all of the cross sections through AB have the same concavity. Then our next task is to figure out what that concavity is. So we look at the second order partial with respect to only x, because that's parallel to the x-axis. That's like a single variable second derivative. So all of those concavity rules follow. And the concavity of that one trace can then be extended to all of the cross sections. And if all of the cross sections are concave up, that means the point AB would be a local minimum. Now we're not restricted to just the second order partial with respect to x. We could also, for both of these here, we could also use the second order partial with respect to y, because it accomplishes the same goal, except the cross section is parallel to the y-axis as opposed to the x-axis. The way to pick is which one's easier, right? So it gives us some flexibility to choose the easier second order derivative to evaluate. Now, if we go through the process and that d value is positive, and now the second order partial derivative with respect to only x is negative, or with respect to only y, that means every cross section through AB is concave down, which means AB is a local maximum. And then if that value is negative, that means the function has a saddle point. And the easy way to understand this is if this value is negative, what that is telling us is at least two cross sections have different concavity. There's one cross section that would be concave up, at least one that would be concave down, so therefore it would be a saddle point like we looked at in the previous graphs. If the value is 0, then the test is inconclusive. So that does not mean the point is not a local min, a local max, or a saddle point. What that means is you have more work to do to decide. And typically that work revolves around some sort of algebraic manipulation. Maybe it's rewriting the function in a specific way, making a comparison, looking at some cross sections, whatever it might be, but you need to find another tool to make that classification. Hopefully that doesn't happen too often, and that we're just focused on these first three cases. So now let's classify those critical points that we found earlier. So we'll start with all the second order derivatives. So partial with respect to x then x is 6x. Partial with respect to x then y is negative 6. Partial with respect to y then y is 2. We don't need to find the other mixed partial. We could, it's negative 6. But again, under Clairaut's theorem, they're going to be the same. So we set up our matrix. So we have 6x, negative 6, negative 6, and 2. So then take the 2 by 2 determinant. So 12x minus 36. And now we need to test our critical points. So we have 0, 0, and 6, 18. So if 0, 0 goes into this expression, it would be negative. And if that value is negative, that means we have a saddle point. And if 6, 18 were to be plugged in here, we would have 72 minus 36, so that's positive. Now remember, we have a choice. We need to pick one of the second order derivatives, either x then x or y then y, so either here or here. In this case, the second order partial with respect to only y is easier since it's a constant. So we say, okay, second order partial with respect to y then y is also positive. So remember what that tells us. The D value being positive means all of the cross sections have the same concavity. We looked at 1, it is concave up, so all of the cross sections would be concave up. This is a local minimum. All right, so there's the complete process for finding the critical points and classifying them. Let's look at a few more examples to get comfortable with the mechanics here. Okay, so find and classify the critical points of this function. So we'll start with our first order partial derivatives. So 4xy minus 4x cubed. Partial with respect to y is 2x squared minus 3y squared plus 1. Setting both of these equal to 0. Deciding where to start. Going to start with the partial with respect to x, since there is a factor that can be taken out. So 4x and then y minus x squared equals 0. So that means that the first order partial derivative is equal to 0 when either x equals 0 or y equals x squared. So this breaks us into a case study. So we have to consider both of these cases when we're moving into the partial with respect to y. Okay, so we could say if x equals 0, under that case, we would get negative 3y squared plus 1 equals 0. So that would be 1 equals 3y squared, 1/3 equals y squared, plus or minus 1 over the square root of 3 equals y. So if we create a list of critical points, our first two are 0, 1 over the square root of 3, 0, negative 1 over the square root of 3. Now we have to consider our second case. So if y were equal to x squared, so that's going to be 2x squared minus 3x to the 4th plus 1 equals 0. All right, not the greatest equation. We can move everything to the right side. So 3x to the 4th minus 2x squared minus 1. Hopefully you're comfortable with a little factoring here. So 3x squared, x squared, minus 1 plus 1. Yeah, that would work. First factor will not give us any real solutions. The second factor would give us x equals plus or minus 1. So adding to our list of critical points, positive 1, and remember this is the case where y equals x squared, so if x is 1, y is 1, and then x is negative 1, y would be positive 1. So this particular function has 4 critical points. Now we have to classify them. So we start the process by finding all of the second order partial derivatives. So that's going to be 4y minus 12x squared. The mixed partial is going to be 4x. And the second order partial with respect to y again is negative 6y. Okay, so we set up the Hessian matrix. So 4y minus 12x squared, 4x, 4x, negative 6y. We take the determinant of this 2 by 2 matrix. So negative 24y squared plus 72x squared y minus 16x squared. So we bring over our list, so 0, 1 over square root of 3, 0, negative 1 over square root of 3, 1, 1, negative 1, 1. So we have to test all 4 of these points in this expression that we got. So if we plug in 0, 1 over add 3, so we get 1/3, so negative 8, 0, 0, so negative 8. So that means that is negative. So this point is a saddle point. Testing 0, negative 1 over rad 3 would be the same thing because we're squaring the y, so negative 8, 0, 0. So we have another saddle point. 1, 1, so that's going to be negative 24 plus 72 minus 16. So 72 minus 40, that's going to be positive. Then we have to decide to look at either second order partial with respect to only x or with respect to only y. Again, the y one's a little bit easier here. So fyy, that is, if y is 1, that's going to be negative. Okay, so that means that the cross-section is concave down, means all of the cross-sections are concave down. That point would be a local max. And then at negative 1, 1, it's going to be the same because we have all squareds except that y, yeah. So greater than 0, fyy is going to be negative, so a local max. So we have 2 saddle points and 2 local maximums at the critical points for this function. So our next example is natural log of xy minus x minus 4y. So this function now incorporates a natural log function. So let's see how that changes things. So we start with our first order partials. So 1 over xy, partial with respect to x is y, minus 1. So cleaning that up, 1 over x minus 1. And then partial with respect to y is 1 over xy times x minus 4. Cleaning that up, 1 over y minus 4. So the first thing to pause and notice is x and y are in the denominator in each of these first order partial derivatives, so we do have to consider the case where they're undefined. Before we do that, let's look at the original function. Natural log functions bring a domain restriction. So if we look, and I'll underline the whole natural log, the domain restriction here tells us that the product of x and y has to be greater than 0, right? That's the domain of a natural log function. The input has to be greater than 0. So that does restrict x and y from being 0, right? Because if x were 0 or y would be equal to 0, those points would not be in the domain. So that saves us a little bit of effort here because there are not points that would make either of these first order partials undefined. Okay, so something that had to be considered because we do have that denominator with variables in them, but looking a little bit more closely at the domain, we avoid any critical points that would make these undefined. So then we shift our focus to that first requirement, which is setting the first order partials equal to 0. So we have 1 over x equals 1, x equals 1. 1 over y equals 4, so y equals 1/4. So we only have one critical point at the point 1, 1/4, which is in the domain because 1 times 1/4 is greater than 0. Now we have to classify it. So now's a good opportunity to pause the video, try this part of the process on your own, play the video, and see how you did. Okay, so I took that opportunity to write out all the work. So here you can see the second order partial derivatives, set up the Hessian matrix. The determinant of that 2 by 2 matrix would be 1 over x squared y squared. Critical point of 1, 1/4. So that value is positive. Then we look at either second order partial derivative with respect to either only x or only y. In this case, I chose only x. That's negative. So that means the cross-section through this critical point is concave down, which means all of the cross-sections are concave down, and that point is a local max. Our last example, a little bit of a word problem just to see how things change and how we would approach it. Find the points on the surface 2x plus 4y plus z squared equals 19 closest to the origin. Okay, so the first thing that we're missing is a function of 2 variables that we are going to optimize. Now, what is it that we are trying to optimize? We're trying closest to origin, so that tells me distance, right? We're focused on distance. Distance formula, if we're going to the origin, right? So distance is equal to the square root of x minus 0, y minus 0, z minus 0, so I'll just write x squared plus y squared plus z squared. Now, that is still 3 variables, but this is where the surface comes in. We can isolate z squared here. So we can say that z squared equals 19 minus 2x minus 4y. And we can replace that in the distance formula. So x squared plus y squared plus 19 minus 2x minus 4y. Now, that's okay. We can call this our function of f of xy and find the critical points of that. One thing that could be helpful, if we think a little logically here, distance, minimizing distance, would be the same as minimizing distance squared. Okay, so we can write this, right? The minimum of d is equal to the minimum of d squared, right? And think of it in terms of values. If the smallest distance is 2 between the point we're finding and the origin, then all of the other distances, if we square them, would still be larger than 2 squared, right? So the benefit of this is we get to eliminate the square root, which makes all of our differentiating much simpler. So this is not a step you need to take, but if you understand this step, it just prevents some challenging, messy differentiation. So we're going to focus on this. So the function that we're going to minimize, f of xy, is going to be x squared plus y squared plus 19 minus 2x minus 4y. Okay, so we're in the problem a little bit to make it easier on ourselves. So instead of minimizing distance, we're minimizing distance squared, but logically that should find us the same exact critical points. So now we start the process that we've been doing in the previous examples. First order partials, so 2x minus 2, partial with respect to y is 2y minus 4. Set them equal to 0. So we get x equals 1, y equals 2. We need our Hessian matrix. So instead of finding them separately, let's go straight to the matrix. So the derivative of this with respect to x again would be 2. With respect to y would be 0. With respect to x is 0. And with respect to y again is 2. So that value is 4. So the nice thing here is we have a critical point. We know that the d value is always positive. Right? So 1, 2. That's always positive. We can look at either xx or yy as far as the second order partials go. Doesn't really matter. They're both the same here. They're positive. So this does confirm that we have a local min. Now the only thing that we're missing, right, we've confirmed that the point 1, 2 will give us the points that are closest to the surface. We need points on the surface. Right? That's the only part we're missing. Find the points on the surface. That means we need a z coordinate as well. So all of our work really was in finding the x and y coordinates of the points on the surface that were closest to the origin. And now our last step, which is an additional step, we can go into our equation here. So z squared equals 19 minus 2 minus 8, since the point was 1, 2. So z squared equals 9, z equals plus or minus 3. So the points we're looking for that answer the actual question would be the points 1, 2, 3, and 1, 2, negative 3. Okay, so definitely a little bit of a variation here, a bit of extension because of that word problem format. And we started with x, y's, and z's. We condensed to x and y's to go through the process of optimization, but then we had to extend back out to find z values. Right? But the main focus of this video is finding those critical points, which the math isn't always easy. Sometimes we break down into a case study. We refer to this as non-simultaneous systems of equations. They don't always work nicely like some of those systems that you're familiar with in earlier math courses. And then the second derivative test. Finding all of our second order partials, finding the determinant of that matrix, and using that to come to conclusions based on each critical point, right? And as I mentioned earlier, it's all based on cross-sections and their concavity. More practice makes this a little bit easier, and I'll see you in the next video.